Hello, everybody, and welcome to this session where we will look at some simple proofs in mathematics. Now, these are problems from a college textbook, but these do cover the simple concepts that we have looked at over the past few months, and they're not involving any rocket science. So I'm pretty sure all of you should be in a position to at least understand these problems. If you have any questions, you can please ask me. So. Here are so these are sample problems from the University of Illinois discrete structures textbook, and we will be looking at simple numerical proofs, most of them involving just algebra and some simple proving techniques. So some of the proving techniques that might be needed in this could be induction or proving by contrapositive or proving by contradiction and things like that. So those are all things that you're aware of, but in case you're not aware of those things, I will just um, repeat or recap what those do. To prove something by contradiction, you assume something which is a contradiction and which becomes a contradiction later to your assumption, and then you kind of say that okay, that assumption was wrong, which means the other thing has to be correct. So it's kind of, if this is false, then it implies that the other thing is true. You're all aware of that. Proving by contrapositive is something which it might be new to you. We'll look at it if it does come up. Proving by induction is where you assume a base case and then you do an inductive hypothesis, and you say that if it works for inductive hypothesis, it has to work. If it works for the next number to the inductive hypothesis, that is k plus 1, then it has to work for every possible number. That is again a very broad definition of induction because I've done it in previous classes, so I don't want to take up a lot of time on it. So let's look at this problem. Use proof by contrapositive to prove the following claim using your best mathematical style and working directly from the definitions of odd and even. You may assume that odd and even are opposites. For all integers p and q, if p squared times q squared minus 4 is odd, then p and q are odd. You must begin by explicitly stating the contrapositive of the claim. Okay, what is the meaning of contrapositive? Contrapositive says that if a statement A implies a statement B, okay, I will explain it carefully, but just let me say the first definition. If statement A implies statement B, then the negation of statement B should imply the negation of statement A, which means if I say that if I am hungry, I will eat food. Okay, statement A is if I am hungry, statement B is I will eat food. Then the negation of statement B, which means if I am not eating food, that should imply the negation of statement A, which will be then I am not hungry. So the original statements were if I am hungry, I will eat food. Now I'm saying the opposite of B should also imply the opposite of A. So I'm saying that if I have not eaten food, then it means I was not hungry. This is a intuitive to understand in real life. If A implies B, then the negation of B should imply the negation of A. Negation is the opposite statement. Okay, we don't have to go very much deep into these definitions and look at the technicalities. This is all that is required. But this particular statement is slightly tricky. It says that for all integers p and q, if p squared multiplied by q squared minus 4 is odd, then p and q are odd. Now we have to prove this, but they have said that use proof by contrapositive. So we have to use the contrapositive proving technique. So let us start by trying to rephrase this statement in a contrapositive way. So which are the two statements that we have here? Statement A is this, p squared times q squared minus 4 is odd. Okay. Statement B is p and q are odd. This then is very important. Somebody's microphone is on. Can you please turn it off? Okay, this then is very important because it talks about implies. We are not saying that p times p squared times q squared minus 4 is odd, p and q are odd. We are saying then p and q are odd, which means this statement is implying this statement. They are connected to each other, which means the negation of this statement should also imply the negation of this statement. You might see in the question here that they have said that you may assume that odd and even are opposites. Why have they made this statement? Because when we try to do the negation of this thing, we will be doing the opposite of this statement. So we'll be doing something which will involve the opposite of odd, right? We'll try to convert this into something regarding even numbers. Same for this one. Why have they said that you may assume that odd and even are opposites? Because if you assume something is opposite of another thing, it has to be a valid assumption. I cannot say that a cat is the opposite of a dog. But because they have said that we can assume that odd and even are opposites, we can use that. Otherwise, we would have to prove why odd and even are opposites of each other. Opposites meaning if something is odd, it cannot be even, and if something is even, it cannot be odd. But luckily, they've said that we can make that assumption, which means we don't have to spend time in proving that odd and even are opposite. So first, let's try to find the negation of this statement. P and Q are odd. Your first guess might be that the negation of that statement is P and Q are even. Well, that is only 50% correct. Because to negate this statement, what's the meaning of negate? Negate is to give a statement that is the opposite of this statement, or to come up with a contradiction to this statement. If somebody tells you that P and Q are odd and you want to negate their statement, you don't have to say that P and Q are even. You can just say that P or Q is even. Because if at least one of P and Q is even, P or Q is even, this statement is disproved. So to come up with a negation to a P and Q statement, we just have to say P or Q is odd. I hope you are able to understand this. Because even P and Q being even is a contradiction, but we don't have to make such a big assumption that both of them should be even. We can say that even if one of them is even, then it's a contradiction to this statement. Because this statement is saying that P and Q are odd. So my negation of that statement will be P or Q is even. So if I have to write B implies A, I will start by saying that if P or Q is even, in fact, let me actually write that here. Okay, so the original statement is now, the original statement was A implies B. So now I'm trying to write the negation of B, that will be not B, should imply not A. So not is just the negation of that statement. So say if P or Q is even, then, so this symbol tells then. Let's look at the exact wordings. If P or Q is even, then P squared times Q squared minus 4 is even. Why is it even? Because we are doing the negation of that. The original statement said P squared times Q squared minus 4 is odd, then P and Q will be odd. But we are doing the reverse of it from B implies A. We're saying if P or Q is even, then P squared times Q squared minus 4 should also be even. Okay, this is the negation to A. I hope this is not that difficult to understand. You don't have to worry too much about why this contrapositive thing actually works, but just assume that this works. Say that if A implies B, then the negation of B should also imply negation of A. So in this case, the original statement was if p squared times q squared minus 4 is odd, then p and q should be odd. Now we are doing the reverse of that. We are saying if p or q is even, then p squared times q squared minus 4 is even. Now let's try to prove this. So if p or q is even, it means either p is 2k or q is 2k. Yes, Shreyan?
Contrapositive.
What's that?
Let's go back.
Shreyan, can you please wait for... What's that? I cannot hear you. Your audio is not working, but can you please wait for me to finish the proof? Thank you.
Yes.
Okay. So if p or q is even, it means that either p has to be 2k or q has to be 2k, because even number is something that can be represented as 2k. So what happens in this case? We have a product here which is p squared times, oh, this is not p2, this is p squared, sorry about that. So this is p squared and q squared minus 4. If this is case 1, if p is 2k, then p squared is also 2k, because a square of an even number is always going to be an even number. Thus, p squared times q squared minus 4 is also 2m, where 2m is another number. Well, let's say it's even. We'll just say it's even to reduce the difficulty and putting all those variables, is even, because if this is an even number, this product is also going to be an even number, because an even number multiplied by any number is still going to be even. Now, if you are not convinced with that, I can still prove it to you, but I'm assuming that all of you know that an even number multiplied by anything is going to be an even. Whether this is odd or this is even doesn't really matter. In case 2, if q is 2k, if q is 2k, then again q squared is also even. Q squared minus 4 is also even, because this is the difference of two even numbers. And if you know that if you add two even numbers or subtract two even numbers, you will still get an even number always. And it's easy to understand, because this is 2 times something and this is also 2 times something. You can take 2 out of the equation and make a bracket, use the distributive property, and you'll get another even number. So if q squared minus 4 is even, thus p squared times q squared minus 4 is also going to be even, because we don't care what p is, because this number is even. Even number multiplied by anything is even. Hence proved. Now remember, we proved the contrapositive. We proved that not B implies not A, but because we did that proof, we can say that hence A implies B. This is proof by contrapositive, not contradiction. Proof by contrapositive. Okay, take a pause for a couple of minutes, and if you have any questions, please type it. Shreyan, wait. Type it in the group. I will read the question and I will answer it, because sometimes the audio is very unreliable. You can just type your question in the group and I will try for the best of my abilities to answer it. Okay. So the original statement was this, and we proved the contrapositive, and hence our proof is done. Okay. I'm waiting for your doubts.
Sir?
Yes.
Okay, so when you told us that you're taking the contrapositive of that, can you go to the earlier question so I can refer to it?
Okay.
The wordings. Yes. So when you told that taking the contrapositive, okay,
Okay.
The actual statement is saying it is the form A and B, then B and C.
No,
Right?
no, we are not saying
From
if A and B, then B. No, no, no.
if
See, this statement is
no
A,
if just if tens are integers,
and this
it will be
statement
the
is
same
B.
thing, right?
Shreyan,
So if
can you please wait
no,
for me to finish the class? Because this is a recording and I'm uploading it. Your voice is not audible. Please try to type your question. If you cannot type it, then please do not speak. After the class is done, you can ask your questions. Okay? I'm assuming that all of you were clear with the concept, and we will go to the next problem. Okay. This involves some new concept, which again, I don't think is too hard for you to understand. So I'll try my best to explain it to you. Prove the following claim using your best mathematical style and the following definition of congruence mod k. Now, I am thinking if this problem is going to be a little harder for you to understand, but I will tell you this much. Don't look at all of these things. Meaning of congruence, for example, I can say that 20 and 25 are congruent to each other mod 5. I know that if mod is a new word to you, just try to understand like this. 20 and 25 are similar to each other if we look at them from the point of view of the number 5. Why is that? Because 20 is a multiple of 5 and 25 is also a multiple of 5. But I can also say that 21 and 26, 21 and 26 are also congruent to each other when we look from the point of view of 5, because 21 is one more than a multiple of 5 and 26 is also one more than a multiple of 5. So they're similar to each other if we look at them from the point of view of 5. Okay, let me give you another example. The number 12 and the number 22 are congruent to each other when we look at them from the point of view of 10, because 12 is 2 more than a multiple of 10 and 22 is also 2 more than a multiple of 10. Just to make sure you understood the concept, I will ask you a problem. Can you tell me if the following things are congruent? Okay, the first thing is 23 and 30 mod 7. So mod 7 means from the point of view of 7, you can think of it that way. Next one, 100 and 200 from point of view of 10. And the third one I want to give is 19 and 27 mod 3. Okay, the first case, are they congruent to each other when we look at them from mod 7? Okay, good, because this is 7 times something plus 2 and this is also 7 times something plus 2. The next one, 100 and 200 mod 10, yes, because they are also, both of them are multiples of 10. And the last case, they are not congruent to each other mod 3, because this is 1 greater than a multiple of 3 and this is a multiple of 3. Now how do you actually check? Suppose we have two huge numbers, okay, we have extremely large numbers and we don't have the time to divide and check the remainders and all of that. How do you do that? You just subtract these two numbers and you see if you'll get a multiple of this number. You just subtract these two numbers. You do 30 minus 23, you get 7. 7 is a multiple of 7. You do 200 minus 100, you get 100, which is a multiple of 10. You do 27 minus 19, you get 8, but 8 is not a multiple of 3. But why does this technique work? Because suppose I am starting at a number which is some numbers away from a multiple of 3 or multiple of 7, whatever that. Suppose it's a multiple, maybe it is 1 more than a multiple, maybe it's 2 more than a multiple, whatever it is. I know for a fact that from this point of time, if I add 3, it will still remain congruent mod 3. If I add 6, it will still remain. If I add 9, because if this number was 2 bigger than a multiple of 3, then even if I add 3, I'll get another number which is also 2 bigger than a multiple of 3. So adding the multiples of the number which from whose point of view we are looking at it, it will preserve the congruency of the number with respect to this number, whether that is 7, 10 or 3. I'm trying to keep it very simple. Okay, hope you understand that. So what are we asked to prove? So let's not look at this particular thing now. Okay, we will look at that later. We will first look at this particular thing. It says for all integers x, y, p, q and m, x, y, p, q and m, these are all integers. Remember, these are some integers. You don't know who they are, but they're just integers. With m greater than 0, that's very important. M is greater than 0. If x is congruent to p, this 3-line symbol means congruent. If x is congruent to p mod m, what does this mean? This is similar to the examples that I showed you. Let's say this is 100, this is 200, this is 10. This is some number. It's congruent to this number from the point of view of this number. And y is congruent to q, again mod m, which means y is some number, q is some number. They are congruent to each other from the perspective of m. Then we have to prove that x squared plus xy, x squared plus xy will be congruent to p squared plus pq, again from the point of view of m. Take a deep breath and wait for a minute before you just say that this is extremely difficult. It's not. This is looking so complicated because these numbers are variables. We are not seeing simple numbers like 100 and 220. If the same problem was given to you where you have 2, 3, 5, 6, 7, it would not look that complicated. So let us see what to do with this. Now let's look at this particular definition here of congruency. The same thing that I explained to you. How do we explain it mathematically? It says that x is congruent to y mod k if and only if x is equal to y plus nk. Before this looks complicated, let me tell you, this is the same thing that we just did. We're saying that if two numbers have to be congruent to each other, then their difference has to be a multiple of that particular number. So in this case, we are saying that if 23 and 30 are congruent to each other mod 7, then it means that 30 minus 23 should be a multiple of 7. Therefore, we can say that 23 is equal to 30 plus some multiple of 7. In this case, that multiple is negative. It is a minus 7. Or you can also say that 30 is equal to 23 plus some multiple of 7. In this case, you can say that 100, or we'll do the reverse, we'll say 200 is equal to 100 plus some multiple of 10. So if two numbers are congruent to each other, you can write them like this, where say one number is the sum of the other number plus some multiple. I hope this is intuitive, because if you add a number which is not a multiple, then the modulus will change, the remainder will change. If here this is a multiple of 10 and we want to keep a number which is a multiple of 10, the only way we can do it is by adding some other multiple of 10. So we can say that x and y are congruent mod z if x is equal to y plus kz, where k is some arbitrary integer. Okay, it has to be an integer, it cannot be a rational number, remember that. So this is how we define congruency. This is just a simple definition of congruency. Even if you don't understand what this means, you can use this equation to solve this particular problem. Even if you don't know the meaning of modulus, or if you're not able to understand this equation, just use that particular equation and let's try to solve this. So what have they given us? They've said that x is congruent to p mod m. So this is the first thing that they have given. So always it's important to note down the simple things that have been stated in the problem so that we can write that again in a more understandable language. So x is congruent to p mod m means that x is equal to p plus what? K times m. The same thing that I did here, I'm changing the variables because this problem is for x congruent to p. So if x is congruent to p mod m, where m is some number like 3 or 10 or whatever that is, from the point of view of this number, it means that if both of them have to be congruent to each other, then their difference has to be a multiple of this number. So if you take p to the other side, then x minus p becomes km or whatever that is. Okay. So this is the first thing that they've given us. X is equal to p plus km. What is the next thing that they've given us? They've said that y is congruent to q mod m. Y is congruent to q mod m. This is the next thing that they've given. So we can say that y is equal to, why is this doing this? Okay. Y is equal to q plus, I could use the same letter k, but I don't want to say that this k is the same in both the cases. So I'll say that, let me say g m. Y is congruent to q mod m, which means y is equal to q plus a multiple of m. I am not using the same letter here because I don't want to give the impression that both of these numbers have the same multiple of m which is being added, which might not be the case. This could be 2, this could be 10, okay, but they can be the same. We're not saying. So these are the two statements that have been given to us, and now we have to prove that x squared plus xy will be congruent to p squared plus pq mod m. We have to prove this. Let me just write these things properly. X squared plus xy is p squared plus pq mod m. This is congruent. Let's use the same definition of congruency. What is the definition of congruency? If x and y are congruent mod z, it means x is equal to y plus kz. So this is x, this is y, this is z. Do not get confused by the x and y here with the x and y here. X and y are two numbers that are congruent to each other. In this case, our first number is x squared plus xy, and our second number is p squared plus pq. They are congruent to each other mod m. So now we can write this as x squared plus xy should equal y plus what? Some number. I don't want to use g or k because they've already been used. I'll say t m. We have to prove this, because if these two things are congruent to each other, it means this is this plus a multiple of m. Okay, what do we do now? Let us substitute the values of x and y from what we got in this particular thing that they gave us. So x squared becomes p plus q the whole squared. Okay, sorry, not p plus q the whole squared. What is x is equal to p plus km the whole squared? I'm sorry about that. P plus km the whole squared. Y is q plus gm, so x times y becomes p plus km multiplied by q plus gm. I'm sorry if this is looking a little complicated. It is just that there are too many letters here, but don't get confused by the letters. Just look at the terms. There was x squared, there was x, there was y. So I wrote x squared, x and y. This should equal this. Okay, we will look at that later. We will first try to simplify this. This becomes p squared plus km squared. Actually, there's a bracket here. Km squared plus 2 p k m. I'm just using the a squared plus a plus b the whole squared formula. A squared plus b squared plus 2ab plus distributive law. Let's just multiply. This becomes pq plus pgm. What is that term? Okay, pgm plus qkm plus kmgm. This is what it becomes. Okay. Are you guys with me? I just simplified the problem. I just opened the bracket. Okay. Now what do? I will write this. So I will write this term first. I'll say p squared. I will also write this term here because I know that these terms are not having m in them. And now I will write all these terms that have m in them. I'll tell you why I'm doing it. Plus this guy, and this guy. All the three of them have m in them. Okay. I wrote p squared, pq. These two things are exactly the same. I have just rearranged the terms to make it simpler. So p squared, which was here, pq was also here, and then km squared, 2pkm, pgm, qkm, kmgm, all these guys together. Now I know that all of these guys are multiples of m because in each of them we are multiplying by m. So what I will do is I will just take out m outside and I will write all these guys together as some t. I'm not interested in what that t is because I know that these are all multiples of m, and I know that m can be taken outside from this. This will become m times something plus m times something plus m times something plus m times something plus m times something. The something is different, but they're all natural numbers. They're all integers, let's say, because we have used only integers in our problem. There is no rational number, there is no irrational number. So all of this I can say that these are all multiples of m. So just to make it simpler, let's say that m was 5. Okay, so all these other numbers are something k, p, g. They are all some other number. This is something times 5 squared. This is 2 times something times 5. This is something times 5. This is something else times 5. This is something else times 5 squared. They are all going to be multiples of 5. So we can say the sum of all of this should be 5 multiplied by something. What have we proved? We just proved that x squared plus xy was p squared plus pq plus tm. The same thing that we wanted to prove. So we proved that x squared plus xy, if it's a number, it will be congruent to p squared plus pq because p squared plus pq plus tm can become x squared plus xy. Shall we actually test this fellow with some numbers as our example, just to see if this actually works out in real life? So which are the numbers? We have x, we have p, we have y, we have q, right? We have only 4 numbers. Is that right? Let me just check. It's not going to be too long at all. It's going to be very short. So we have x, y, p, q, and m. Okay. Let me say that. So now x has to be congruent to p. So give me 2 numbers. So let's pick our m. What should be our m? Let multiples of which number? Let's think of 5. That's always easy to understand. Let's say our m is 5. Remember, m is the number from whose point of view we are looking at. So let's think now we are 5. Okay, we are suddenly 5. Everything that we see around us, we are looking at it in terms of how they are related to multiples of 5. X has to be congruent to p mod m. So let me say that x is 23 and p is 13. They are congruent to each other in terms of 5 because m is x is 3 more than a multiple of 5 and p is also 3 more than a multiple of 5. Then now let me do y and q. They should also be congruent to each other in terms of 5. Why is this doing this? Okay, anyway, y is I'll say 47 and I'll say that q is, was that q? Okay, q is 32. Quick question. Are 47 and 32 actually congruent when we look at it from point of view of 5? Or does this look wrong to you? Why is it? Because 47 is 2 more than 45 and 32 is 2 more than 30. So they are just the same thing. So what did they say? They said that x squared plus xy will be congruent to p squared plus pq. We are not worried about the proof now. We have already proved it. We'll just test if the proof actually works. What is x squared plus xy? X squared plus xy. Oh my god, this will be 529 plus what is 23 times 13? That will be 299. Xy is 23 times, no, sorry, x squared plus xy. Okay, so that's 23 times 47. Give me a second. That should be 1150 minus 69, which is 1081. Okay, should be congruent to p squared plus pq. P squared is 1024 and pq, sorry, p squared, not p squared is 169. Sorry about that. 169. P is 13. P squared plus pq. Pq is 13 times 32, which is 416. Okay, I am not sure if my mental math was right, but let's just check. 529 plus 1081 should be 1610, and this is 169 plus 416 is 585. They should be congruent to each other mod 5. Are they congruent? Yes, both of them are multiples of 5. We picked two. I just randomly picked some numbers and now we got multiples of 5. Actually, I didn't even have to do the addition. 9 plus 1 was 0 and 9 plus 6 was 5. So both of them had to be multiples of 5. Okay. On this happy note, I will stop the recording and I am done with the problems that I wanted to explain for the sake of this lecture. And now I will clarify all your doubts.